So in the second session of the sample preparation part of our fracture toughness testing, we are going to discuss a few things today. One is side groups, and another is how do we calculate the K1c value for CT as well as SENB specimens. And once we do this, then I will share some data with you from the experiment, and you can do the analysis. That will be the first part of it, and then we will also go to J integral calculation from experiment for CT and SENB specimen, and we will also try to calculate the J delta A curve, so JR resistance curve, but that we will not discuss in today's class. Okay, so now let us proceed with our basic idea which we had from the last sample preparation part. For the CT specimen, we had the dimensions for that, where this was 1.2 W, where W is the width of the specimen measured from the center of the holes, which is the load line. So from here till end is W, and this length is 1.25 W. There are of course tolerances, and then you have thickness, which is B, and W is usually 2 times of B only for CT specimen. So there are tolerances when you are making this kind of a specimen. If you give the design to the sample manufacturer or in workshop, you have to give tolerances, which is very important. So now we have the specimen, and before we load it, we have to do pre-cracking. We discussed pre-cracking part in the previous session. So we formulated that how much amount of K max we can apply in order to have a crack growth of for the fatigue part, so to make the sharp crack. And we also knew that the crack length, the fatigue part of the crack, so the initial crack length is actually A because of the notch plus A because of the fatigue pre-crack. And so notch is from the center, whatever is this distance, that is the notch distance, and then we have some fatigue pre-crack part. So this part is AF and this part is AN, and the total of these two is called the initial crack length, A naught. But for fracture toughness calculation in plane strain using LEFM, linear elastic fracture mechanics, we don't expect much of a crack growth, okay, because we ensure by putting a lot of criteria, which you remember from MM302, that the material has to be very brittle. Otherwise plasticity is too much, and then we cannot apply linear elastic fracture mechanics. Right, so we have this initial crack length, and the fatigue pre-crack part should at least be 1.3 millimeters. Okay, so so we have to do significant amount of fatigue pre-cracking so that we have significant amount of sharp crack at the tip. Why do we have sharp crack at the tip? That also we have discussed. You see, if English's stress intensity factor says that whatever stress you apply, that gets intensified across an elliptical or penny shaped crack, which is like this, and this is 2A, and the minor axis of the ellipse is 2B. And from the linear elastic fracture mechanics, we know that the stresses at the crack tip go infinity, right? So what should be this elliptical shape when the stress, according to English, will touch infinity? In order to do that, you have to make this thing zero, approaching zero. And when that thing will be approaching zero? When this becomes very sharp. Okay, so when this dimension comes closer to zero, then we have a very sharp crack, and we cannot achieve it by manufacturing process, so we make it by fatigue pre-cracking. Right, so all those things we have discussed. How much should be the load for fatigue pre-cracking, so the K max, and then we do the fatigue pre-cracking, and then we have this crack. But usually in plane strain fracture mechanics of thick specimen, and in this case we have to have thick specimen because we have to follow this criteria. So we have to have thick specimen, right? So let us say that if the fracture toughness of the material is 100 MPa root meter and our sigma naught is 200, then this is just 1 by 2. So 2.5 into 1 by 2 whole squared will be 2.5 divided by 4, right? And this is in meters, right? So so this will be how much? This will be 5 divided by, so this will be 5 divided by 8, right? And that will be 10 divided by 16. So that becomes 0.625 meters, right? 0.625 meters, and if I multiply this by 1000, then I get 625 millimeters, right? So 625 millimeters is a very big thickness. So in 1 feet we have approximately 300 millimeters. So you have 2 feet thick specimen. 2 feet thick specimen is huge specimen. 2 feet thick specimen is huge specimen. Okay, because for 2 feet thick specimen, B is 2 feet, W is 4 feet. So you see the sample is approximately of the height of a human length, and that kind of sample you have to, I do not know how will you carry it to the lab and what kind of machines you should have to test it. There has been machine, those who can afford it. So this is this looks very bad for testing one property from such a big specimen to make such an effort, right? That's how the integral came into picture. And now this K1c is kind of obsolete, but still it is used for ceramic materials and some of the brittle polymers and bones and other things. In bones still K concept is applied. Sometimes even in simulation it is ignored that the material in the bone can actually deform plastically. It can actually deform plastically. It is not very brittle like glass. It is not. But but people use it because the amount of plasticity is very less, and people try to simulate dynamic conditions for bones, so like impact, crash, falling down on the street. Those kind of simulation has a dynamic loading. If you load it very slowly, then the material will have time to, and we know that polymer has tendency to deform in time dependent manner. Bone has a lot of part which is ceramic, so which is carbonate, and that is why linear elastic fracture mechanics and a lot of calculation based on just the elastic strain is carried out, but that is not accurate. Anyways, so we have we know now that we should have fatigue pre-crack, and we have a very thick specimen. But in thick specimen, initiating a fatigue pre-crack is a challenge. So I have this as kind of a specimen, right? And this is very thick. And then I load it. I load it by putting a pin inside. And we fix this one or pull this one and pull both up and down. Usually fix the lower one, pull the upper one, and that's how. And then you load it in cyclic loading, so pull push, and that's how you will initiate the fatigue pre-crack. But there can be a lot of inhomogeneity in the material. You can have inclusion here, you can have not inclusion there, or you can have a lot of inclusion here, you can have a big inclusion there. There is some inhomogeneity inside the material which we do not know, and because of that a fatigue crack might initiate here first. Usually if there is no inhomogeneity, the crack initiates in the center first. Why? Because the constraint at the center is very high. Yeah. So but if because of any inhomogeneity, the crack can initiate somewhere else from the center, so it can initiate at the surface, and then the crack will propagate like this. It will open like this, so in 3 dimension, and this part is still is closed, and this part has opened up. This part has opened up because of fatigue. It will not look this big. I'm just trying to explain what will happen. So it will open up, and once you know there is a weak point, it remains the weak point. So crack has propagated, and it will keep on propagating like this. And so if you somehow can look at inside from the top, then you will see the crack is actually growing like this maybe. Okay, so on the one surface you will see only this much pre-crack, on the other surface you will see this much pre-crack. Okay, so to avoid this and to so because we have a lot of constraint that we shouldn't increase the K max too much in the fatigue pre-cracking part, because that will cause compressive residual stresses, right? And we don't want to have any effect of fatigue pre-cracking on the fracture toughness. So we have a lot of criteria which asks or demands the test to be to have the pre-cracking part at a lower value of K max or K. Because we have so lower value of K, sometimes it is not possible that fatigue crack will initiate, and initiation of fatigue takes a lot of time. 80 to 90% of the time is consumed in the initiation part of fatigue. Once it is initiated, it propagates well, but initiation takes a lot of part. And in order to promote initiation at lower value of K and to avoid this asymmetry, there is a thing which is made manufactured. So this, you don't need to do any other sophisticated matter. This can be done by manufacturing process, and it's called chevron notch. Okay, chevron notch is something which I will explain you here. I'll try to explain here. So this is the notch crack tip, right? This is the usual notch crack tip in a CT specimen. This is what you manufacture. If you look in 2D, right, it looks like this. This is the notch which you make, right? Now, what chevron is that, now let us look at this one. So let us look at this one. So let us look at this one from the top. So from the top, if you look, it will look like, so it will look like this. Yeah, so this is the part till here, and this is the part here. And because this is upper at an upper surface, so it should actually look bigger because it is on the upper surface. We cannot make the height in 2 dimension, but try to see it like this. The thing which is closer to us will look bigger in comparison to the thing which is away from us, right? So this part is closer to us if we look at from the top, and this part is away from us. So you see what is this? This part is this part, right? All right. So now what is chevron? Chevron is something like this. From the top we are looking. So chevron is something like this. Okay. So I shouldn't have done it. Yeah. Chevron is something like this. And this angle is 90 degrees. Okay. So this point is a point. It's just a point. Okay. I hope you can visualize what is this. So it is like this. So this is usually how your notch is, and then here you have something like this. Okay. So if you look at from the side, you will have something like this, and that, and this. So this is the chevron which is coming. Okay, so this is the chevron. So you have the notch till here on the surface on both sides, and inside you put the wire EDM like this, and you remove this much amount of material. You remove this much amount of material by wire EDM, right? and the depth of that wire is this. Okay, so you have something like this. The advantage of this is that this tip is under too much amount of triaxial constraint. There is no material here, there is no material there, right? And this point is at the center, so you have a lot of constraint here, and when you load it cyclically, it is very high stresses are there, so a crack will initiate at the center, so it will avoid asymmetry, which may cause something like this. So it will avoid this kind of phenomena because it ensures that the crack will initiate at the center and then it will propagate like this. So this chevron will open up, okay, and then you can have whatever 1.3 or whatever amount of fatigue crack you want to have. Okay, so that is the importance of chevron notch. This is something which we do before doing the pre-cracking. Okay, so when we make the sample, now this is hung. Okay, so where are the dimensions? Yeah, so when we give the drawing to the manufacturer, apart from these dimensions, we also include chevron. We also include chevron drawing here and the details of that the included angle is 90 degrees, and if you put it 90 degree, then what is that distance that you can give to the manufacturer, and you will get the sample with the chevron notch. Once you get it, then you load it for pre-cracking, and then you have this much amount of pre-crack, and now your sample is ready. Not yet, there's one thing remaining. Okay, so after chevron notch you have the sample. Now you have to do side grooving, and side grooving has a lot of importance. And side grooving, let me tell you what side grooving is, and then we will discuss what are the advantages of side grooving is. So side groove is, as the name suggests, it is a groove which is made on the sides of the specimen. And why do we make it? We will discuss later, but let us now look at what side grooves are. Okay, so this is my specimen. Well, there can be a chevron, doesn't matter, but we have this specimen in 3 dimension. Yeah, this is the specimen in 3 dimension. In one of the tutorials I will show you in an abacus the geometry of the specimen with side grooves, how it looks like. You can have images also. Actually we can look at the images. But let me tell you what chevron notch is. Okay, so chevron, so this is our sample, and now look at the sample from the back side. It will look like this, right? It simply looks like this, and that is our thickness of the specimen, right? Side grooving is making a groove here. So remove this part, and also from the other side. Okay, so remove a triangle from the sides, remove a triangular section from the side. Okay, so then it will look like this. Can I delete? Oh, this square is not getting deleted. Yeah, now it will get deleted. I hope it doesn't make a square. Good. No, it does. Okay, don't make it a square. And now let me delete here, delete there, and it looks like this after you make the side groove. Okay, so from the back side it looks like this, and you have removed the thing from here. Okay, also from the other side, so this side and that side, both you have removed. Okay, this is called side grooving, and the standard says that you should have side grooving included from both sides. The side grooving should not be more than 0.25 of the thickness, so 1/4 of the thickness. You should not groove it more than this. for many materials 0.2 of the thickness has been found to give satisfactory results. Okay, so 0.2 B is recommended, but nothing more than 0.25 B is allowed. Okay, so this is what side grooving is. And so you see this image, you see this one, and I do not know if it is clear, but let us see if we can find something. Oh, this is a paper, so okay, so this is the specimen, and you see this part here is the side groove. Okay, this is how it looks like in reality. This is how it looks like in reality, and in simulation I don't think they have form side grooving. Okay, no problem. And if you look at the so in the drawing you can probably see how it looks like. Yeah, yeah. So you see here, this is the drawing of the side groove. Okay, and here there is no side groove. So here there is side groove, here there is no side groove. Okay, so this is the side groove. And let us also see chevron. Let us also see chevron notch. Okay, so the real picture of chevron notch should be somewhere. I could have given you the picture of my specimen, but here I don't see. Here I don't see the chevron notch. Okay, so broken specimen. So broken CT specimen. Let us see if we don't get any real images. We don't get any. Yeah, see here you see, but this is I think a smaller picture is not available, and you need to pay money for that. Anyway, so can I expand it? Yeah. So you see, this part is the chevron notch, and this part is the stable crack growth. Fine, that we'll see later. And this whole thing has opened till here because of fatigue pre-cracking. Okay, so this is how chevron looks like in the sample. All right, so now we know about side groove and we know about chevron notch, right? And now so why do we do side grooving? So we do side grooving because if you don't do side grooving, so across the thickness, if we don't do side grooving, okay, so let me draw another sample which does not have yeah, okay, good. So this is a sample from the back side where we don't have side grooves. Okay, and now if I plot the stress, which is in this direction, and thickness direction is usually Z direction, and the upper direction is y direction. Okay, so if we plot sigma zz, then that is 0 at the surface, because surface is traction free, you don't have stress there. And as you go in the center, you have the maximum amount of stress, right? So sigma zz profile looks like this. Okay, and so you see why you have a lot of constraint here, because here at the center you have sigma xx, sigma yy and sigma zz all in the maximum value. Okay, so this is the profile of sigma zz, and because of this the crack will grow. If I cut the sample from here and look at from the top, then the crack, so if this is my initial crack length, initial crack tip, this is my initial notch tip or crack tip, fatigue pre-crack tip, yeah, and then I loaded the sample and the crack grows. So the crack grows like this, crack grows like this. Okay, and why it grows like this? Because you have more constraint in the middle, so the crack first initiates in the middle. Okay, and at the surface you have lesser stresses, so it initiates at the lower stress, and then it propagates like that always, because this situation never changes. Always you have crack, you have stress at the surface lower than in the center, so crack always takes this form instead of having a flat crack front which is moving, right? So the problem which happens is that what is the crack length? How much is the crack length? Is the crack length this, or the crack length is this? Okay, so you will take some average value, but average value doesn't mean that the flat crack is propagating. Well, average value would mean that the average crack length is something like this, and that is propagating. Whatever is the average of these two, or if you take many number of points and take an average, then right, but that is not the real situation. So to avoid this, to avoid the plane stress region at the surface and to have plane strain which is in the center, let it have through and through thickness of the specimen, this side grooving is done. So what it does is that this side grooved part increases the amount of stress at the surface. Why? Because this groove is actually like a crack. It is a notch, basically. It is not a sharp crack, but it is a crack, right? And this crack will also increase its stress field. So you actually will have plastic zone here also and here also. Okay, so you are increasing stress by making grooves on the sides, and when you make this, then the broken sample is like this, right? And the crack usually more or less is flat, right? And later it can take this kind of shape, of course, because no, but actually no, this is wrong. I have side grooving throughout the length of the specimen. So it is like this, and this is how it will look like. Yeah, because the lower part is away from us, so that will look down, and the center part is here. So this part is this surface. Okay, this surface. This is this one. Okay, so this part is removed and this part is removed. Okay, so the crack will be parallel, more or less. When it grows, it will be parallel because of the side grooving. So this is the benefit of side grooving. Okay, now the thing is, when to do side grooving. Side grooving is done after pre-cracking. Okay, so you make the sample with chevron, and then you start pre-cracking, right? And then you have certain amount of pre-crack here. After you have done pre-cracking, then you ask the manufacturer to take the triangular part out. Okay, take this part out of the specimen. Why are we doing such kind of thing? Because if we do the side grooving first, then we will not be able to see where the fatigue crack is growing. Okay, and in metallic materials we do it by seeing, by naked eyes, not by optical microscope. Unless your sample is very small, we don't use microscope. It is visible with the naked eye. You just put a torch on the sample and you will see the fatigue crack, pre-crack growing, moving. So you will see this length. But if you do the side grooving first, then you will not be able to see it. Yeah. So what can happen is that fatigue crack might grow in this direction because of some reason. Usually it shouldn't happen, but because of some reason the fatigue crack might deviate and you will not be able to see it because you have side grooved it, right? So you cannot see what is happening in this region, and only when the crack will pass, then you will see, oh, the fatigue crack, pre-crack has deviated and now your sample is bad. Now you cannot use this sample. So this sample has gone. It is just to scrap. Okay. So first do fatigue pre-cracking, then do side grooving. And once we have done this, once we have done all this thing, so once we made the sample, we made the chevron notch, then we did the fatigue pre-cracking, then we removed the side materials by doing side grooving. Okay, and for side grooving the angle should be anything smaller than 90 degree. Anything is smaller than 90 degree. Don't make it much shallower. More than 90 degree will not increase the stress too much. Okay, so when we are making shallow, when we are increasing the included angle, actually again we are going to English formulation, 1 plus 2a by b, and by increasing the including angle we are actually increasing the b. Okay, but we also don't want to make it very sharp. We shouldn't fatigue pre-crack in that direction. That will be very complicated first of all, and even if you do it, you will not be able to see it. You can only see it what is going on the backside. Anyways, let's not go there. So that is not the standard practice for pragmatic reasons. Okay, so now our sample is done. Now our sample is made. Okay, fine. Now once our sample is made, we have loaded it. Okay, we loaded the sample in the machine. We loaded the sample in the machine. Yeah, and it's a brittle sample, a crack initiated. So we will get from the experiment, we will get the force versus load line displacement plot. Okay, we'll get this plot, and this plot looks like this. This plot can have three different shapes. So it can have this kind of shape, which is type 1. It can have this kind of shape, type 2, and it can have this kind of shape, which is type 3. Okay, so once this is done, you stop the test. It doesn't mean the crack has propagated through and through. It will be somewhere there, but your point of testing is done. After that, what you do? After that, you again put it under cyclic loading. Okay, and break the remaining part of the sample and make two pieces out of it. The question is, why are we breaking the remaining part in cyclic loading? Previously, what people used to do is they used to put ink at the tip of the specimen. So as the crack grows, the ink goes inside and it takes the color of the ink. After that, you break it just by pulling the sample, and you know how much amount of crack opened up when you were testing. Okay, so this much amount of crack was created when you were oh, this much. Oh, this is eraser. I not have a brush. Should have a size. Yeah, so So this much amount of crack was because of the testing, the fracture toughness testing, and my ink color was green, so this will look green to me. And after that I broke the specimen just by pulling it. So I will not see any color here, I will just see the green color there, right? Because ink will not propagate that much and you remove the ink after breaking it, so you will see, you can demarcate how much amount of crack growth actually happened during the testing, right? And you can measure this. But then ink actually interferes with the material's fracture toughness, because ink acts as a corrosive environment, okay? Because you will have water in it or some kind of organic liquid or inorganic liquid, and that creates that corrodes the specimen, and it affects the fracture toughness value. So then it was stopped, it was banned, and then people started using another phenomena which is still people use, and that phenomena is, once you have done with the testing, you say that fine, this much amount of crack growth is okay for me, I don't want to proceed with this. So then you heat the whole specimen to, let's say, 200-300 degrees Celsius for 30 minutes. Okay, you heat it and then pull the specimen so that you make two pieces of it, and then you look at it and you will see that this much amount is, so this amount which was already opened, because of heating it will get a different color, a reddish yellowish color, because of heating. Okay, and the remaining part you broke after heating it, right? So this part was not open, so this will not have this color. So this phenomena is called heat tinting. Okay, you give the tint by heating, and that's how you know how much amount of crack growth happened in the type of testing, right? Fine. So we can have three different types of force displacement curve, broadly speaking. In this case, in type 1, what is happening is that a stable crack growth is happening. Yeah. In type 2, there at certain point there has been a very fast crack growth, so it is called pop in. Okay, so snap, a crack opened up and it propagated, so load went down, but after that it again acquired a stable cracking. In type 3, what happens, you have a continuous pop in, that means it's a catastrophic failure. In this case, crack initiated and propagates like anything. Usually in metallic materials, if you have a purely brittle fracture, the crack propagates with the speed of sound. So this is why it is called catastrophic, because in metals the speed of sound is also very high, it is 2000 meters per second, something like that. So once you have in a brittle material, if you have a crack which is propagating, nobody can stop it. It is like glass shattering. You cannot stop it and the structure will fall down. Okay, so you don't want this kind of phenomena to happen. So you can have broadly these three type of curves, and if the specimen is CT specimen, then so type 1, type 2, type 3, what do we do with this? In type 1, type 2 and type 3, in all three cases, the standard recommends that you plot a 5%, you find out the slope of the linear part and they decrease the slope by 5% and draw a line from the origin. So 5% will not look this big, but I'm just drawing it to tell you how it will look like. Okay. So this is called 5% second line. You do the same thing here and do the same thing there. Okay. So wherever it intersects the type 1 curve, that is called PS. Okay. And you draw a straight line following the initial slope and let this point intersect horizontally with this one. Okay, and this distance is XS. Okay, and now you find another point at 0.8% of PS. So let us say it is here. So it is 80%. So 0.8 of PS. This here again, let it intersect horizontally with this one, and this distance is x1. Okay, and if x1 is greater than 1/4 of xs, then your material is not very brittle, and your test is not valid for K1c testing. So because linear elastic fracture mechanics is not being followed, the material is over ductile. Okay, what you can do is you can try with increased thickness, but that anyways. In the second case, what you do is you do the same thing what you did here. Okay, repeat the same thing. If you get this kind of curve, only difference is in this case this point is taken as PQ. In this case, PS is my PQ when this criteria is followed. If x1 is less than 1/4 of xs, then PS is a valid load value, which is PQ. In this case, the maximum value is PQ, although you will do the calculation like this for finding out x1 and xs. Okay, and in type 3 also you find out doing this, and again this is your PQ value. Okay, what do we do with PQ? We have PQ value and we have the specimen dimension. Now we find out KQ. What is KQ? KQ is expected or potential value of K1c. We will make it K1c only when all the criteria are satisfied. Okay, so till then it is the potential fracture toughness or expected fracture toughness. So KQ is calculated using this formula. So load, which is PQ, divided by the thickness into W to the power 1/2, and then there is a function of A by W. There is a function of A over W. Okay, so PQ we know, thickness of the specimen we know the width of the specimen, and we can calculate F of A by W. F of A by W is a very cumbersome formula. It comes from finite element calculation, or it is called plastic collapse calculation, or plastic load calculation, limit load calculation. Yeah. So F of A by W comes from limit load calculation, but that's a different topic. We will not go there, and it requires a lot of FEM, and that is one application of FEM which you can find out here. So F of A by W simply is, because it comes from there, so there is not so much theory here. It is purely a calculation based on geometry and all. So you get a function which has this value. So I will write F, so A by W. So this is A over W to the power 1/2 minus 185.5, A by W to the power 3/2 plus 655.7, A by W to the power 5/2 minus 1017 into A by W to the power 7/2. Okay, and so this is my F of A by W, and using this calculation and using that calculation you find out the value of KQ. Okay, and now you have the value of KQ. Using this KQ, calculate the value of RP. Okay, or instead of RP, you calculate that what is the value of 2.5 into KQ divided by sigma naught whole squared. And if this is if this follows this criteria, then KQ is K1c. If not, it's not. Okay, so this is how you calculate fracture toughness for CT specimen, for SENB specimen, and if you do the side grooving, then you have to do a little change in the formula here. So you actually have to replace the value of thickness with the net thickness value. So what you have to do actually is, if you have side grooving, where is the side grooved specimen? Here. Okay, so if we do not do side grooving, then this thickness is B. If we do the side grooving, then this is our net thickness, which is denoted as Bn. Okay, so if we have side grooving, then here a formula will change a little bit. So this will be PQ divided by B into Bn to the power 1 by 2. Rest of the things will remain same. Okay, rest of the things will remain same. So similarly, in SENB specimen, we should have the specimen dimension, and then we can calculate the value of K1c. So in SENB specimen, the specimen looks like a rectangular bar, and we have a notch here. Okay, this is like this, and we put the loading here, and we fix this part here, and we apply the load from the top. This is how we do it. In this case, we can have something like this, where we put the clip-on gauge, which will measure the CTOD or COD, so the displacement at the crack tip. Or if not, then you always have load line displacement. In this case, load line displacement is simply the displacement here. So the load you are applying is on this line. Okay, so this is my load line, and the displacement, whatever happens, how do you get it? You get it from the machine, right? So the machine has a fixture which is like this, and this fixture is being pushed down, and machine knows how much the actuator is going down. So from there you get the value of displacement, and there is a load cell which tells you how much is the force there. Okay, so you will again get the force displacement curve. In this case, this dimension is simply W. Okay, and this dimension is the total length of the specimen, which is, so total length of the specimen is 4.5 of W. And where do you put the lower rollers? Those are, that distance is called the span of the 3-point bending specimen, and this span is 4 times of W. Okay, so if you look at it in 2 dimension, the thickness of the specimen, let's say, is 10 millimeters, right? So in this case, again, W is 2 into B, which is 20 millimeters. Okay, so this thing will be 20 millimeters. This thing will be 4.5 into 20. So 9 by 2 into 20 is 90. So this is 90 millimeters. Okay, so this is 20, this is 90, and the thickness is 10. So now you have your rectangular piece. Then you create the notch and then a little bit of fatigue pre-crack, so that this distance is A, and A over W reaches somewhere in between 0.45 to 0.55. So usually you try to have it a value of 0.5. Okay, so this is done for SENB specimen. SENB specimen you pre-crack with a load. P max should not be greater than, so it should always be lower than 0.5 into the thickness into the ligament length into the yield strength divided by the span value. Okay, I hope I am dimensionally correct. So this is millimeter, millimeter square, millimeter cube. This is Newton per millimeter square into millimeter cube divided by millimeter. So this is good. So it comes in Newton. Fine. So the load should be lower than this for the cyclic loading. So this is the criteria you apply for pre-cracking, and then you calculate the fracture toughness KQ following the formula of this EQ divided by B as PQ into S divided by B. If you have side grooving, BBN to the power 1 by 2, W to the power 3 by 2, and then you have F of A by W, which is 2.9 A by W to the power 1 by 2 minus 4.6 into A by W to the power 3 by 2 plus 21.8 A by W over 5 by 2 and minus, so minus 32.6 A by W to the power 7 by 2 plus 38.7 A by W over 9 by 2. So this is how you calculate the value of KQ. Okay, and in this case A is simply A naught plus whatever delta A has happened. That is the value of A you use. Here also for CT specimen. Okay, so this is our fracture toughness calculation for mode 1, and from the experiment using for CT specimen and SENB specimen. Okay, so we conclude this here, and I will share some data with you, and I will also tell you the dimensions of the specimen, and then you are supposed to calculate the value of K1c for that data. Okay, so and in the next lab we will discuss with the J integral calculation. Okay, so that is completely different lab, but well, it is a part of fracture toughness. So what you can do is you can make this report for plane strain fracture toughness using LAFM. So you can write it K1c plane strain fracture toughness. You can name the lab report like this, and you can submit it with the analysis of the data which will be given to you. Okay, that is all.